Welcome to Root Labs at Lunch. My name is Bart Moons, facilitating the session today for Frederick. So with Root Labs, we start organizing lunch sessions to share knowledge around topics that relate to artificial intelligence. So every week we have a session, and next week we have 3 Python gurus that will create a Python package in 15 minutes. If you want to check all planned events, you can go to our brand new meetups page. I will post a link in the chat. Questions. Should you have any questions during the presentation, please use the Q&A section in Zoom, and we'll come to the questions at the end of the presentation. So today we have a session around Rust. And well, it struck me, if we have developers that name their cat Rusty, something must be going on. And Frederick, please enlighten us what is going on, and can you introduce us to Rust? It's over to you.
So hello. As mentioned previously, my name is Frederick, and we'll be talking about Rust today. So for those of you who are unaware of what Rust is about, when you go to the Rust homepage, it will tell you that Rust is a language empowering everyone to build reliable and efficient software. And I think this is very much true. This is pretty much the language in a nutshell. And throughout this presentation, I will try to convince you on why this is the case. But before I do that, I will first show a few use cases of the language, what it's good at. So Discord, you might know it, is a very popular chatting service. And in their application, they have a microservice called the read states service. And what this service does is it remembers what messages have been read by whom. So basically, every time you connect to Discord, every time you read a message, and every time you write a message, you are connecting to this service to update some information, to read something. So as you can imagine, this is quite a critical service of them. This needs to work, and this needs to work fast. And so it's not only critical for having a working application, but it also is performance critical. It needs to perform very well. Otherwise, you will see a lot of lag. So their original implementation, or their previous implementation, was written in Go. And when they when they monitored some metrics of this service, what they saw was something like this. So the interesting one here, or the one we'll be focusing on, is the one on top. It shows the average response time of the microservice. So here you see a lot of sudden spikes. When they looked into this, it turned out that this was related to garbage collection. Basically, these spikes were caused by the garbage collector. And this is kind of annoying. One of the most important features of Rust, and we'll go in more depth on this later on, is that it doesn't have a garbage collector and can still give us some safety. So they thought, well, maybe we could rewrite this in Rust, and if everything goes well, we might have similar response times, but just without the peaks, without the garbage collection peaks. And so they did, and this is what they saw. So this is the exact same service, but re-implemented in Rust. And here you can see that the spikes that were present previously in the Go version are now gone because there is no garbage collector. But not only this, but also if you look at the measure that's used for the metrics, you see that average response time previously was measured in milliseconds, and now it's measured in microseconds for the Rust implementation. So performance has really increased quite a lot. And this is one of the main use cases, one of the main powers of Rust, to give you this low latency, high performance kind of application where it can handle a lot of load. Another very interesting use case is something like operating systems. So there are apparently several different operating system implementations written in Rust. Most of them are approved by proof of concepts. One of them, called Redux, is more extensive. You see a screenshot of it here. And basically everything in there is written in Rust, all the way down to the kernel. The kernel itself is also written in Rust. So this is also a very powerful use case of Rust, and that you can go very low level. You can write an operating system with it, but you can also write embedded software, for example. And then maybe something that's also interesting to point out is that for the last 4 years in a row, the Rust language was considered the most loved programming language by the Stack Over Developer Survey. So it has won last 4 years. So now we'll go a bit deeper into the language itself. So there are many reasons why you would want to use the language. I have summed up here a couple of them. We won't go through them now, as basically this presentation will go through most of these. So we'll first focus on the first two. So this is the memory safety without garbage collection that I mentioned earlier. And there is also concurrency without data races. So basically when you try to write concurrent software, you typically run, or you have a chance of running into data races due to shared mutable states. And Rust is giving us a lot of compile time guarantees that will prevent this kind of errors. And we'll focus on these two features at the same time, because a large part of these two features is provided by the same concept, and that's called the ownership system. So in Rust, we have something called ownership, and it's very similar to your intuitive understanding of ownership. So basically, every piece of data in a Rust program is owned by something. And things that can own data are things like functions, structs, and enums. So here we have an example where we have a function A which owns a string. And here we have a little code snippet of a struct point. And this struct has two fields, X and Y, both are 32-bit integers. And so in this case, the struct point owns the two integers. So this is the idea. Now I'll go a bit more in depth on how this actually impacts your program. So here I have a very simple code snippet. We have a function called main that creates a string, assigns it to a variable called text, and then it calls a function called printed, giving it the text, and that function then, well, prints the text. Fairly straightforward. So when we start in the main function, when we enter the main function, nothing is owned by anyone. There is no data yet, so no one owns anything. Both main and printed don't have any data. Then when we go to the first line, we create a string and assign it to a variable. And when we do this, we are basically giving ownership of the data that we created to that function. So in this case, the moment this line is done, main will own the data that's in the text variable. Then what happens next is we call the printed function, and we are giving it the text variable, the text data. And by giving it, we are, again, if you can look at this intuitively, we are giving ownership as well. So we are giving the text data to the printed function. The printed function can then use this to print the text. Nothing changes here related to ownership. And this is something very crucial, when we are at the end of the printed function, and this is something more general, whenever a function ends in Rust, all the data that is owned by that function will be removed. So in this case, the printed function owns the data that's in text, so it will remove that data. And then the program will just end without any data leaks, because the text data has already been removed in the printed function. Okay, so this is intuitively how it works. Now imagine we wanted to do something like this. This is the exact same, except that we are calling printed twice. So we just want to print it twice. What will happen here? Well, I just mentioned that when the printed function ends, we are removing the text data. Now this can be an issue here, because the moment we do the second printed call, we are basically referring to data that has already been removed. Turns out in Rust, this doesn't compile. It will give you a compile time error due to one of its ownership rules. And it's saying that we can't use the text variable here on the second line because we've already given it away a previous time. So that's exactly what we want, because otherwise we would be referring to some garbage data. But okay, so this is nice. We can't do this. That's what we want. But still, we might want to print something multiple times, or just pass variables to multiple function calls. That sounds like a very common use case. So how would we do this? Well, let's look at it intuitively again. Maybe one possible solution is that printed gives the data back, right? So the main could give the data to printed, but when printed is done, instead of removing it, it should give it back. So it won't have ownership over it, but it could borrow it for a second. And this is exactly what it's called. It's called borrowing. So if you look at the printed function now, we are not accepting a string anymore. Like here we are accepting a string. Now we are accepting an ampersand string. Ampersand stands for borrow. So the printed function is now not asking for ownership of a string anymore, but it's asking just to borrow it. And then it prints the text. When the printed function is then done, it will give it back, and it won't remove it because it doesn't own the data. And then the second printed call will work just fine because the main function will have the text data back. Okay, so this is really cool. But why would we do this? I mean, there is usually in most other languages, this would work just fine. Why would we go through the hassle of doing this ownership stuff instead of doing it the straightforward way? Well, one reason is that it gives us guardrails. So here I have a small program. So in most programming languages, you'll have this concept of a file. You can open a file, you can read from a file, write to a file, and you can close the file. And in most languages, the moment you close the file, you cannot read from it again. And this will typically give you a runtime error saying you can't read from a closed file. Using this ownership system we just talked about, we can get this runtime error at compile time using the ownership system. So let's just go through the code here. We open a file called file.txt. We store it in a variable called file. And you'll note that there is this mute keyword. So in Rust, everything is immutable by default, except mentioned otherwise. So here we are explicitly mentioning mute. So we are saying, okay, this file might be changed in the future, it should be mutable. In this case, it needs to be mutable because we need to update an index that shows which bytes have already been read from the file and which ones still need to be read. So to update this index, we need to update the file. Then we just read the contents from the file, we store it, then we close the file. And when you look at the close function, you'll notice it's not asking for a borrow of a file. No, it's asking for ownership of the file. So what the close function is telling us here is, okay, we'll close the file for you. But to do this, you need to give us ownership so we can be certain that you're not doing something with it without us being aware. So in this very specific case, when we then write to read the contents of the file again, we'll get the exact same compile time error saying you can't read you can't use a variable after having given it away. So here you can see how using this ownership system can give us some compile time safeties. Here, for example, that we don't use a file after closing it. I just talked about this mute stuff. So mutability is another concept in the Rust language itself, and it also gives even more guardrails. So here is a very simple program. We have a function called main, which creates a point, and that's the same struct as we saw earlier with the x and the y. And then we pass this point to a function called printing point, which prints the point. But oh no, we made a mistake, and we accidentally tried to override one of the fields of the struct. Well, because everything is immutable by default, the Rust compiler will give us a compile time error saying we can't update this point.x field because the point variable in printing point is immutable. So then we would see the error, we could just remove the line and everything would work just fine. Now imagine we, for some reason, did want to do this. How can we adjust the code so that this does work, so that we can set a point.x to 42? What you need to do is, when you look at the printing point function now, is not pass an immutable borrow, but ask for a mutable borrow. So the printing point is asking for a mutable borrow, and then it can change it. But also in the main function, we need to make some changes. First of all, we need to, again, specify that the variable is mutable. And this is not useful when, this is not very useful when you add it, but when it's not there, that's some very good information. When it's just let point equals blah, 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 then we can be 100% certain that at any point, wherever, this point variable will always be the same. And that's very good to know, because if you pass this point variable to multiple functions, to multiple threads, who knows what kind of stuff you'll be doing, you can still be certain that it's the same as it was on the line you created it. And then we call the printing point function, and we explicitly mention that we want to pass a mutable borrow of the point variable. Again, telling the compiler, yes, we are aware that printing point is asking for to possibly mutate the point, and we're okay with that. So again, here you can see that it's giving, the compiler is giving, is really wants to make sure that what we're doing is what we expect we're doing. But now let's go back a bit. Let's go back to the list of points that I mentioned, the memory safety one and the concurrency without data races ones. So for memory safety without garbage collection, the real gist of it is this thing I mentioned earlier, where when a function ends, it removes all the owned objects. That's really what it's about. There is a bit more to it, because if a function removes its data, it's also important that that data is not borrowed to something else, to another thread, for example, that's running at the same time. We get these guarantees at compile time as well. And that has something to do with lifetimes, but I won't be able to go into this in this presentation. And then for the concurrency without data races, this is a bit more difficult to see. But basically, threads are very similar to functions that can just run concurrently. So if you look at it from this perspective, then you can also see that this ownership system doesn't just work for functions, but it also works for threads. And then thanks to a couple of extra borrowing rules Rust has, I didn't talk about these, but one of the borrowing rules we have is, for example, we can't pass multiple mutable borrows without being certain that the first one has already been given back. Thanks to these borrowing rules and this ownership logic, this ownership system, we can have a bunch of compile time certainties that we don't have any data races going on. The next point I'll be talking about is zero cost abstractions. So this is also a very common term you hear with Rust. So here is some code. Most of it is kind of annoying to read. You don't need to read all of it. You just need to focus on this part. So what this does is it iterates over an array called coefficients, and then it uses some kind of functional API to do something with that array. So it's zipping it, mapping it, summing it, and this map accepts a closure, for example. In other languages, this is known as a lambda, or in some others as a function. So this is a very functional API that you get. Here I have the same, just on a separate slide. So this looks nice and is considered quite pretty in most languages. But in most languages, you'll also be paying for this at runtime. Usually when you really want performance to matter, which we do in Rust, as mentioned earlier, the two main points Rust focuses on is efficiency, reliability. So one may so you might say, well, how about using a C++ style for loop instead of using this functional API? Would this give us better performance? So this for loop would look something like this. So this is the exact same, but without the functional API. But actually, when you compile the functional part and the manual one, turns out that they are just as fast. And actually, in this very specific case, the functional part is even slightly faster. And so this is what we call a zero-cost abstraction. It doesn't mean that this version doesn't cost anything. It still takes some runtime and it still takes memory. But what it's saying is, if we consider the C++ style loop as the concrete implementation and the functional API as the abstraction over that, using the abstraction doesn't come at an extra cost, at an extra runtime cost, and therefore using the abstraction is zero cost. So it's a zero cost abstraction. That's what it means. Here I have another example. So in Rust, we don't have null. It doesn't exist. So if we want to have some kind of notion of an optional value, what we need is something like this. So we have an enum option, option of type, an option of a t. T is a generic in this case, so we can have an option of strings or an option of ints, something like this. And any value of type option will be one of two values. It will either be none, so this is the case where there is nothing, or it can be some and then a value, so something of a type t in this case. So this is this kind of optional value, but it's with a basic compiler. This would be some extra. This will give extra runtime costs, because now instead of just going to the value directly, you first have to go to the option, then check is it absent or is it present, and then go to the value. So you have an extra layer of indirection. And a better approach would be just to use the value itself and use the null case as the non case, you can say. But actually, this option enum doesn't exist at runtime. The compiler is very smart in this way. So the compiler, what it will do is it will translate the none to the null case, which does exist at compile time, of course. And the sum t case will just be translated to the t case itself. So if you want an option string, we won't have this option type in runtime, but we would just have a pointer to some data, which might be null, which is the none case, or might not be null, and that's just the sum case. And so here you can also see how the abstraction is zero cost, given it just compiles down to the more concrete implementation. So those are two very important and good features about Rust. There are also some bad things. Rust has quite a significant learning curve. Usually when you learn a language, there will be a lot of concepts you'll already know. For example, variables, if constructs, if structures, all these things, they're pretty much the same in any language, and so you'll learn very fast. But in Rust, especially this ownership system is very unique. You'll probably not have seen something like this before. So it will take you a while to adjust to this. And in that way, it has a high learning curve. That's an important one. The next bad thing, the next disadvantage is what some people call dancing with the compiler. I and some other people also call it fighting with the compiler. So basically what will happen is when programming in Rust is you will write some code, you will try to compile it, you will get, the compiler will give you a compile time error probably, and the error will probably be related to the ownership system. You made some mistake, similar to what we did before with the two printed calls. We adjust the code. The compiler gives us suggestions on how to fix it. So we fix it. We compile again. We get another mistake. it will probably again be related to the ownership system. We fix it again, and this will probably go on for a while. So in this way, it's kind of a dance or a fight with the compiler. And so we have the last disadvantage. Well, there are more, but these are the ones I thought of. The third disadvantage is the long compilation times. Like I mentioned earlier that we have a very smart compiler here, but for having a smart compiler, you pay with compile time, basically. Another maybe often asked question is, should I use it over something like Python? And in general, maybe not. You definitely can. Rust gives you also a very high level functional API in most cases. So it's definitely, it can be very nice to program in it. It's the most loved programming language. But I would say that in general, Python and Rust are addressing different use cases. So as you saw earlier, the use cases related to Discord and the operating system, you won't use Python for that. And similarly, you won't use Rust. Maybe you shouldn't use Rust to just write some small script where Python will do just fine. Here I have some links to some interesting use cases for Rust. So arewebyet.org shows the current state of web server implementations written in Rust. Are we game yet shows the same for game engine implementations. And are we learning yet the same for machine learning libraries? And this is pretty much the last slide. So if you're interested in learning something about Rust, you just go to rustlang.org/learn. There's a lot of good resources there, a lot of good learning resources. One of them that I particularly liked was the book. That's how I learned Rust. There are some others as well. For example, there is a Rust by example resource where you can learn Rust well by example, as the name implies. You might also want to go to play.rustlang.org. It gives you a web page with a text editor inside, in which you can write Rust programs, and it'll compile and run your Rust programs for you. So if you're just learning Rust, you don't need to install a compiler and an IDE. You can just go to this website. And then if you're a bit more experienced with the language, I would highly suggest to go to the documentation of the standard library. It's a very nice documentation, very easy to go through. And then in this way, you'll learn a bit about what the standard library gives you. And you'll also learn something about the best practices in Rust codes. And then there is RustConf, of course. So this was my presentation. Thank you.
Thank you, Frederick. We have some questions. I will also launch a poll to see what people think about Rust. So first question was, can you recommend resources to learn Rust? Was just before your last slide, so I think you've put that up. And then we have a question from Dorian. For what applications have you used Rust yourself?
So when I did a master's thesis at KU Leuven, and there they made a new kind of machine learning model, which is very similar to a decision tree ensemble, an online decision tree learning algorithm. And they implemented it because it's new. There was no library for this. And they made an implementation. They wrote it in Python, which was very inefficient. And basically, I rewrote it in Rust.
Okay. So I shared the poll, so a lot of people will certainly give it a go, and we already saw people that were using Rust as well. So I don't see any other questions. We will be posting the video also on our YouTube channel. I've put the link in the chat. So should you have any questions while rewatching the webinar, please post them in the comments on YouTube. I would say thank you all for joining, and hopefully we can welcome you on a next Root Labs at lunch. Thank you for joining. Bye.